All right, we are looking at section 2.2, the derivative as a function in differentiability. Yesterday, we were talking about form 1 of a derivative, and we spent a whole lot of time discussing that. But from yesterday, we said that f prime of x is equal to the limit as x approaches c of f of x minus f of c over x minus c. And remember that this is just another form of the slope formula where we really have y2, y1, x2, and x1. Keep writing 2 instead of c. There you go. And then we had all sorts of algebraic problems where we had to factor and FOIL and all sorts of things. There is a form 2 that uses the difference quotient, and this is more like the example that I showed you in Desmos, where the h value was getting really, really small. But you did use the difference quotient in the last unit, and I know you also used it in pre-calculus. So the derivative of a function is given by the limit as h approaches 0 of f of x plus h minus f of x all over h, provided the limit exists. If f has a derivative, then it's said to be differentiable. Now, here's an important note. This form is used when a problem asks you to use the definition of a derivative to find f prime of x. So if it talks about the definition of a derivative, this is the version that you want. This is the more popular version. We'll see it more often. And I used to tell students not to worry about the version that we talked about yesterday. And then we did some released AP problems, and right there it was. So it is important that you know both. So example 1, find the derivative of the function at any real number x using form 2. So f prime of x is the limit as h approaches 0, f of x plus h. So right away, I'm going to take that x plus h and put it in for both x's. So x plus h squared minus 5x plus h minus, now the f of x piece, that's just the original function, x squared minus 5x. And all of this is over h. So what do we do at this point? How do we clean this up? Well, the piece in the beginning, you're going to FOIL. So f prime of x is the limit as h approaches 0. And yes, you should really write all of this out. X squared plus 2xh plus h squared minus 5x minus 5h minus x squared plus 5x all over h. And then with these problems, everything should cancel that does not have an h in it. Every other term should cancel. So positive x squared and negative x squared, negative 5x and positive 5x. Then what you can do is factor out the h. And the reason why that's important is because it needs to cancel with what's in the denominator. So we'll pull out the h of 2x plus h minus 5 all over h. And so when we said cancel, these h's cancel out. I put a 0 in place of the h, and so I'm left with 2x minus 5. And that is the derivative at any real number. Example 2, we're going to do the same thing. So f prime of x is equal to the limit as h approaches 0. I'm going to substitute right away. This is x plus h minus the square root of x all over h. If you put 0 in place of the h right now, you do have 0 over 0. I don't factor this problem, but if you recall, this is a conjugate pair. So I'm going to multiply by square root of x plus h plus the square root of x. Same thing in the denominator. If we were in class together, I would ask, okay, where do you FOIL? You would FOIL on the top in this case. So this is the limit as h approaches 0 of x plus h minus x. The denominator is h, square root of x plus h plus the square root of x. So in the numerator, what cancels out? The positive x and the negative x. I'm left with an h, so instead of rewriting that, I'm going to cheat a little bit and just cancel this h with this h. Now, what's left in the numerator? The limit as h approaches 0. Don't forget, there's still a 1 up here. A few of us forgot that there was a 1 there on the test and let our answer just float up to the numerator. It doesn't quite work like that. And it's not a 0, but it's a 1. Now, if I put 0 in place of h, I have 1 over the square root of x plus the square root of x, which is 1 over 2 root x. The next question, what's the domain of f prime? Well, the domain is your set of x values. We know that. So the domain has to exist for x. But when I look at this function, what's a bad value for x? What wouldn't work? 0, because we can't divide by 0. So it's all real numbers, except x cannot be equal to 0. And then you have to consider the square root. Okay, so what has to be true about the square root? Well, it has to be positive inside. So x has to be greater than 0. So when I put these two pieces together, my overall domain is x greater than 0, and it cannot be equal to 0 because we don't want to divide by 0 in that rational expression. So it's not actually all real numbers, but any values greater than 0. All right, we're going to take a pause there and I have to move to the library. All right, we've relocated to the library, but we're going to keep going here. So example 3, we are going to find, we have the surface area in square meters of a balloon. It's expanding as a function of time in seconds according to the following formula. This is just a formula particular to this situation. That's not true surface area for anything. Find the rate of change of the surface area of the balloon with respect to time. So S prime of t, I'm going to zoom in here a little bit. S prime of t is going to be the limit as h approaches 0. We're going to put x plus h in for the t. So I've got 5x plus h squared minus 5x squared all over h. So again, this is 0 over 0. What do we do about it? You're going to FOIL that first term. So the limit as h approaches 0, I have 5x squared plus 2xh plus h squared minus 5x squared all over h. And distribute the 5. So I have 5x squared plus 10xh plus 5h squared minus 5x squared. And then conveniently, remember anything that does not have an h should cancel. So positive 5x squared cancels with negative 5x squared. And what I have left, I can factor out an h. So s prime of t is the limit as h approaches 0, pull out the h, 10x plus 5h all over h. And these cancel out. I put 0 in place of the h, and I'm left with 10x. So find the rate of change of the surface area of the balloon with respect to time. So surface area with respect to time, which is important for part B. What are the units of s prime of t? Think of the fraction. We have the top and the bottom. It's going to be, what are we in? Square meters. So it's in meters squared per second. Okay. Now, I made one video and I had a technical issue, so I couldn't share it with you. But I was going through these the long way. I'm going to show you a day early because it's such a time saver. And that is the power rule. So for the remaining problems, you have my full permission to use the power rule. It will make your life so much easier. So the power rule for derivatives says this. If s of t is equal to 5t squared, I'm going to use the example that we have. The power rule says that the derivative, I'm allowed to bring the 2 to the front. So I have 5 times 2 and t to the first power. So my answer is 10t. Guess what? We had 10x. I just have a different variable. That's all. All you do, one more time, I know it seems that easy. You bring the exponent to the front, you subtract 1 from the exponent, and you multiply if there's a number in the front. Awesome, right? So that replaces this whole process. Do you still have to know this whole process, the limit definition of a derivative? Yes, you do. You especially have to know how to set it up. Then, once we know the power rule, these problems become much, much quicker. So example 4, we are going to find f prime, but instead of doing this the long way, we're going to use our new power rule. Let's pick a color. So f prime of x is equal to 3x squared. Now the derivative of 1 is going to be 0. So that's my derivative. If we graph both functions, x cubed minus 1 is a cubic function that moves down 1. Looks like this. What shape is 3x squared? 3x squared is a parabola that passes through the origin. So what do we need to take note of this picture? Okay. You want to notice that you have a slope of 0 here. And then that's where the derivative has a 0 as well. That's where it crosses the x-axis. That's not the prettiest picture in the world, but you get the idea. Now, example 5, use the graph of the given function to create the derivative. So here's the important stuff. This point has a horizontal tangent line, which means the slope is 0. So if the slope is 0, the derivative has a value of 0, of -2. If I look at this point on the right, I also have a horizontal tangent line. So I have to have a derivative value of 0. Oops, 3/2. So I'm going to do 1.5 like this. Now, let's talk about slope. Let's use another color. Over here, I have an increasing function, so my slope is positive. So my graph has to be above the x-axis, the graph of the derivative. In between these 2 points, I have a negative slope that's going downhill, so it has to go below the x-axis. And then all the way over here, I have a positive slope, so it has to be up here. So my derivative is a parabola. I know that's not super perfect and we will need more practice, but we will. Another point to consider is this point right here, where you have a y value of 0. Or, yeah, I have a y value of 0. I switch, and we'll talk about this more later, but that becomes the low point right here. Okay. Sorry about the extra noise in here in the library. Just because something's continuous does not mean that you can find the derivative of it. So each of the following functions, f prime of 0 does not exist. Your absolute value, this is where it fails to have a derivative, is right there at the vertex. The next picture, we have a vertical asymptote. It fails to have a derivative with a vertical slope because remember, rise over run, if we have a number over 0, it's undefined, we have a vertical asymptote, so that's not going to work. And then finally, x to the 2/3. This is called a cusp. When you have those two curves like that, and we don't have a derivative at a cusp. So for a function to be differentiable, it must be continuous, and that limit as x approaches c must also exist. Now, here's a note. If it says, if a function is continuous, nope, I said it backwards already. If a function is differentiable, then it is continuous. So before we were looking for the function, they had to come right out and say it's a continuous function. Now, if the problem statement says the function is differentiable, now you think, okay, so I can find the derivative everywhere, therefore it must be continuous everywhere. Example 6, determine if f prime of 1 exists for the following function. So we're going to use that power rule again because it's so much quicker. So we're going to check the left-hand side. And we know that that is the first piece. So f prime of x is equal to -4x. And if we try the value of 1, f prime of 1 is equal to -4 times 1, -4. And then we're going to try the right-hand side. Okay, so here's the right. f prime of x is equal to 2x. That's my power rule. I'm going to bring the exponent to the front. So f prime of 1 is equal to 2 times 1, which is 2. So -4 and 2 are not equal to one another at all. Now, there's another thing that we should check, and it is true here. You should check to see that the y values are equal, and they are. If you substitute a 1 into both of these, you get a 2 in return. So it's continuous. So the limit from the left is equal to the limit from the right. So the function is continuous, but it's not differentiable because these two slopes are not the same. Okay. Now, if we look at example 7, show that f of x equals x minus 2 to the 4/5 is not differentiable at 2. F prime of x, and again, we're not going to go through that long rule, especially on this one, is 4/5. X minus 2, that quantity stays the same. I subtract 1 and I get a -1/5. So how did that happen? Just remind you of your middle school fractions. 4/5 minus 1 is 4/5 minus 5/5. So this is a -1/5. You'll get quicker at that as we go, no worries. And then if I rewrite this with a positive exponent, it moves to the denominator. So x minus 2 to the 1/5. Why is it not differentiable at 2? Well, it's not differentiable at 2 because if I use a 2 in place of x, I have a divide by 0 error. It's undefined. So x cannot be equal to 0 when we talk about the derivative. It's a continuous function everywhere. It can exist up here. We could use the 2, that's no problem. But for the derivative, we cannot. Example 8, determine if each of the following piecewise functions is differentiable at C. Well, you got to do two things. One, you have to make sure it's continuous, and 2, then you want to check to see if it's differentiable. So we are going to do the left side. I am going to find f of 3 on the left-hand side. Think of your limit. This is technically a limit idea. So if I substitute 3 in for my x, I've got 2 times 3 plus 2 is equal to 8. Now I want to do my derivative. So f prime of x is equal to 2. There's no place left to substitute the 3. So that's my derivative. Then we'll do the middle. Again, you want to check your actual function value. So f of 3 is equal to 5. That's this middle row. You can't really take a derivative there. It's a point. A derivative has to kind of be on the left and the right hand side of the point. And then we'll check out the right hand side, which is here. So f of 3 is going to be 3 minus 1, which is equal to, and so f prime of x is equal to 1. Now, it's continuous, but not differentiable. Actually, no, it's not. It's none of the above. Determine if each of the following piecewise functions is differentiable. 6, 8, no, not continuous, not differentiable. So because of this, it's not continuous. And on this one, because the derivatives don't match, it's not differentiable. So all of the above. All right, we had a quick break in there. Sorry about that. Now we are going to do the same thing for part B. One, you have to make sure it's continuous, and this is our last problem. One, you have to make sure that it's continuous, and 2, you have to make sure that the derivative matches on either side. So we want to check the left-hand side. I'm going to do f of 0. My left-hand side is really 0 cubed. F prime of x is going to be 3x squared. Remember, that's that magic power rule. And if we put a 0 in place of there, f prime of 0 is 3 times 0 squared. So this is also 0. A lot of zeros in this problem. Then if I try the right-hand side, f of 0 on the right is 0 squared. which is equal to 0. F prime of x is equal to 2x, and f prime of 0 is equal to 2 times 0, which is 0. So lots of zeros all over the place. But what do they really mean? Because these two are the same, it's continuous. And then because these two derivatives are the same, it's differentiable. Now, I just want to show you real quick. X cubed and x squared. Well, it's kind of boring. But x cubed is the graph to the left of 0. And then x squared is the graph to the right of 0. So that's your full parabola. So it almost looks like the original x cubed graph. There you go. Go ahead and try problem set 2.1. Tomorrow, we are going to have time in class to go over everything in 2.1 and 2.2, and then we'll learn 2.3 on Thursday. So I know this isn't ideal. Thanks for being patient.
Can we just check to make sure that's live? Like if I create it, just say, just hit all buttons.